table of the KB values. So for water, the KB is equal to 0.15, and notice the units, degrees Celsius per molal. Okay. Lowercase m, molal concentration, moles per what? Yeah, kilogram of solvent. Right, solvent? And then the other thing here is lowercase I, which is what we call the Van't Hoff factor. We're going to look at this in more detail. The Van't Hoff factor takes into account the number of particles that arise from a given solute. So if we put sodium chloride in solution, that breaks apart into sodium ion and chloride ion. So for every one sodium chloride, we get 2 particles. And so that I is going to take that into account, and I'll show you how. Okay. Does everyone see why the boiling point is going to increase? Right? The vapor pressure has lowered for the solvent. It means there's less gas molecules for that solvent. The pressure has lowered, but the definition of boiling point is when the vapor pressure is equal to the atmospheric pressure. It's going to take more energy, more heat to get to the boiling point. We can, very similar, right? IKBM for the boiling point. Look at that using a phase diagram. Phase diagrams are chapter 10, oh, nope, 11, I believe. Sections 5 and 6, maybe. There's a link in the ebook as well. So if you're reading this chapter, it'll link you to the phase diagram section. So for our phase diagram, we're going to have pressure on our y-axis, temperature on x. And if you look at the solid line, okay, we're dividing the line between liquid and gas. This is going to have to do with the vapor pressure, okay? And also, if we go to our x-axis, the boiling temperature. So at 1 atmosphere, we have the boiling point of pure solvent. If we add solute, that line is represented by this light blue line. Again, there are fewer solvent molecules able to get to the gas phase. And that boiling point then is elevated, okay? So we're looking at a difference in the temperature here for the solvent and here for the solution, okay? Questions on that? Vapor pressure lowering, boiling point elevation, definitely related. So now we have freezing point depression. Freezing point depression and boiling point elevation, if you look at their equations, elevation, IKFM for freezing point depression. Pause right here because I think your book uses something slightly different. I'll have to check this for me. I think the freezing point depression equation has a negative sign in front of it, minus IKF. I usually don't include that in my equations. Number one, then there's a negative sign. I don't know, it's just a choice. But it makes me remember the concept, okay? So if we have boiling point elevation, you know that the temperature has to increase. It's going to be a positive change. If we have freezing point depression, compared to the solvent, the freezing point has to decrease. So it's going to be a negative sign. So if you remember the concept, you don't even need to worry about the sign. But I do believe your book, and I saw some nods, so it probably is correct, that your book uses delta TF equals minus I K sub F M. You can decide which one you want to use. Okay? They both work. You just got to remember, if you don't use the sign, if it's freezing point depression, it's lowered, it's negative. its boiling point elevation is increased, it's positive. I don't know what equation you'll get on the exam. I've asked, but I don't know yet. Okay. Again, the change in freezing point, delta TF, is going to be the difference between the freezing point of the solvent and that of the solution. K sub B is a freezing point constant for the solvent. Again, tabulated values. For water, it's 1.86 degrees Celsius per molal. And then, of course, the molal concentration. And we have another Van Hoff factor here. So, yes?
So if we're asked to solve for moles in the freezing point depression equation, will we be given the Van Hoff factor? Because the post-lab asked us to solve for it, but didn't give us I.
Okay, so if you are asked to solve for molal?
Just for moles.
For moles, okay. Using the molal concentration to solve for moles, would you be given I? Is the question. And I don't know exactly what is expected on the post lab, but I have an answer for what you'll see in lecture and on the exams. If you are given the value for I, we're going to talk about this in more detail, then definitely use it. If you are not given a value for I, we need to consider if the solute is an electrolyte, a salt, or a non-electrolyte. That piece of information you'll be given. If it is a salt, and you're not given a value for the Van Hoff factor, you're going to estimate based on the maximum number of particles that can form from that salt. If you're given a value, obviously you put that in there. Does that help? Yeah. Okay. Other questions? Did you talk about ion pairing in your lab? Sort of? Yes? Small amount. Okay. We're going to talk about that. Let's see. Okay, so we'll go ahead and start talking about ion pairing then. So again, colligative properties dependent on that total concentration of solute particles. And I said before, with the example, if we have sodium chloride, solid, we put that in solution, we get sodium ion and chloride ion. Okay. For every 1 sodium chloride, we get 2 ions total. So if we have a solution that's 0.1, let's do molal, NaCl. In solution, we'll have 0.1 molal sodium ion and 0.1 molal chloride ion. For a total of 0.2 molal ions. So I'm simply adding those concentrations. And this is that factor. For every 1 unit of sodium chloride, we get 2 ions. The I is accounting for that. So you don't actually need to, when you're calculating molality, you don't actually need to do this type of calculation because the I is accounting for that. I, Van Hoff factor, accounts for this. Okay. But there are many cases when the solutes can experience, I guess we'll say, ion pairing. And this is where the sodium ion in this case and the chloride ion sort of move close enough together that it affects their effective concentration. So they can basically form what's referred to as an ion pair. If we look at this solution, this diagram of a solution or picture of a solution, we have our chloride ion, our sodium ion. These ones are ion paired. And if we were to try to, this figure is a little hard to do, but if we were to try to look at the number of water molecules effectively around each of those ions in the ion pair, it would be lower than the ions that are not paired together. And so that's why there's some sort of effect that takes place when we have ions that are close enough together in solution to form these pairs. It affects the number of water molecules around them, which therefore affects the concentration of those solute molecules or particles. So this one ion pair has a reduced amount that it can affect the solution. Does that make sense? All right, so I mentioned that there's a predicted value for number of particles in a solution. I can't see that. There. So here's a table with Van't Hoff factors and different concentrations of these given solutes in a solution. Sucrose is a non-electrolyte. So for every one sucrose you put in solution, you get one sucrose in solution. Non-electrolyte, doesn't break apart, it's not a salt. Everything else on this list, these are all electrolytes. Okay. So when we put those in solution, they're going to dissociate. So we can relatively easily predict the limiting value for I, for the Van't Hoff factor. And again, if you're not given a experimental value of I, use the limiting value. So our limiting value of I for sodium chloride is 2. 1 sodium, 1 chloride. If we take a look at the effect of concentration, we'll see that as the concentration increases, the Van't Hoff factor value decreases, because we have more ion pairing. So as we go from low concentration to high concentration, we have more ion pairing, which decreases that Van't Hoff factor. Does that make sense? Okay. What would you predict the limiting value of K2SO4 to be, potassium sulfate? Anyone? Yeah. 3. Why is that? Dissociates into 3 ions. You're going to have 2 potassium ions and 1 sulfate ion. Remember all of the polyatomic ions from 1210 or whatever Gen Chem type thing you've done before? You're going to want to remember those. Magnesium sulfate, MgSO4, limiting value 2. Make sense? So we're going to have for that one magnesium 2 plus and sulfate 2 minus, SO4 2 minus. All right, but let's take a look then. Well, questions here. So if we look at the completed table, we can kind of look at some trends. Again, with increasing concentration, so going from right-hand side of the table to left-hand side of the table, we're increasing our concentration. We'll see that the Van't Hoff factor decreases. Again, more ion pairing. But let's take a look at sodium chloride and compare it to magnesium sulfate. Let's look at the 0.1 molal concentration. The Van't Hoff factor for sodium chloride is 1.87, and for magnesium sulfate it's 1.21. Why do you think they're so different? There's some options. What's that? Ion size? Higher charge. Those are of these three options. Yeah, so we're looking at the effect here of ion charge. When we compare sodium chloride and magnesium sulfate. The greater the magnitude of charge on the ions, the greater the chance of ion pairing, the greater attraction. Okay? So let's put that in here for ion charge. Whoop, that's not a thing. So at the greater magnitude of charge, we have more ion pairing. More ion pairing, Van't Hoff factor decreases. Ion size, though. Ion size might be a little bit more difficult to think about. If you have a smaller ion, it tends to have more ion pairing. And I think that has to do with the ability to get other ions in close proximity. So for a smaller ion, we have more ion pairing. And we saw the effect of concentration. It's pretty clear from this table. As we increase the concentration, the Van't Hoff factor decreases. I decreases. And that's because we have more ions in solution. They have a greater chance of interacting with each other. And more interactions. So if we increase the concentration, ions are closer together, more ion pairing. Does that make sense? Cool. What solution were you looking at in lab? Well, I think only half of you have done it, right? Sodium something? Sodium acetate? No, there are 4 others too? Wait. Okay, wait. Did you do freezing point depression? Oh, 5 things. 4 things. 3 salts in water. Oh, okay. That's a lot. What? How long did that take? That take 3 hours? No? Really?
It took 2 hours to froze water.
Longest to freeze?
Yeah. Good.
You know why?
Yeah.
All right, that's fair. All right, let's regroup. Maybe someday I'll visit you in lab, but not on Monday. Which is all That's my excuse. Okay, so let's do some things here. So let's take a look at these 5 different solutions. Well, one's not a solution, one's pure water. And let's rank these from lowest freezing point to highest freezing point. And for the first round here, let's ignore ion pairing. So take a look at those. I'll figure out where I am in my notes. Anyone, how would you feel? Closer? Which one of these will have the highest freezing point? Yeah. Pure water. Great. Let's put that one in right away. Okay. Now, when you're looking at these other solutions, we know water is going to have the highest freezing point because everything else has a solute, and its freezing point is depressed, so it's lower. We've got sodium chloride, we've got sugar, we've got magnesium chloride. I mentioned sucrose on the last slide, a couple slides ago. Sucrose, sugar, same thing, non-electrolytes, right? So for the sugar solution, I equals 1. Okay. What about for sodium chloride? Again, ignoring ion pairing. I equals 2. And for magnesium chloride, I equals what? So 1 magnesium ion, 2 chloride ions. Great. So in our equation, we have our Van Hoff factor, of course, I. We've got K sub F, right? Freezing point, what do we call this? Freezing point constant. And then the mole-al concentration. We're given the mole-al concentrations. We aren't given K sub F. Doesn't matter. We could look that one up, but it doesn't matter, right, in this case, because everything's in aqueous solution. I guess I could have stated that more clearly in the problem. Everything's in aqueous solution. Kf is the same for each of these solutions. Okay. So we really only need to multiply our Van Hoff factor by the mole-al concentration and compare those values to figure out which one's going to have the highest or the greatest change. Okay? The one with the greatest change is going to have the lowest freezing point, right? Does that make sense? Okay. So given that, which one is going to have the lowest freezing point? I'm going to lay on somewhere else. Magnesium chloride, yeah. The 0.2 molar, right? Mole-al, excuse me. So if we multiply 0.2 by I, which is 3, we get 0.6. Then the next one, is going to be our sodium chloride. We have 0.2 molal, and we have I of 2. Is that right? Yeah. NaCl. And then our 0.3 molal sugar solution. Again, I is 1, multiply I by the 0.3 by the molal concentration. And which leaves our 0.1 molal sugar for the last slide. Questions on that? Yeah?
Why was water the highest freezing point again?
Water is the highest freezing point because it's the pure solvent. And anytime we add a solute to the pure, it's going to decrease the freezing point. So even if it's really dilute, it's still going to decrease that freezing point. So the solvent's always going to have the highest. It doesn't matter if you have a series of solutions and they're all in the same solvent, that solvent always has the highest freezing point. Yeah.
So was magnesium chloride the lowest one because it had like the highest Van Hoff factor?
Yeah, basically. So, well, the Van Hoff factor definitely plays a role in why magnesium chloride has the lowest freezing point, because we have to multiply that Van Hoff factor by its concentration. Now, let me propose another solution. What if we have 0.4 molal sugar? Where does that go? Again, we're going to ignore ion pairing. It's going to be tied with the 0.2 NaCl solution, right? Again, I for sugar is 0.1, so it would go here. Make sense? Okay. Now, what if we, let's ignore this, let's ignore the 0.4 molal sugar. But for everything else, let's include ion pairing. Let's say it can happen. But I'm not going to give you the values. I don't care for actual calculation right now. Let's think about how these values will change. So we know that magnesium chloride can have ion pairing, right? Ions are formed in solution, therefore it can't have ion pairing. What is the maximum value of I times the molal for the magnesium chloride? 0.6, right? That's the maximum. 0.2 times 3 is 0.6. If we include ion pairing, I would say that this is the answer. The answer for the I times the molal concentration is less than 0.6. Right? For sodium chloride, 0.2 molal NaCl, I times the molal is less than 0.4. Okay? Why am I doing this? Now if we look at that 0.4 molal sugar, I times molal is what? Still 0.4, right? Sugar is a non-electrolyte. I will always be equal to the number of solutes, right? So I is always 1 for a non-electrolyte. So if we have two different solutions and we want to figure out the one with the lowest freezing point, we have a solution that's 0.2 molal sodium chloride and one that's 0.4 molal sugar. Which one is going to have the lowest freezing point? The sugar, yeah. I guess I just kind of want to show you that both concentration and the Van Hoff factor are important when you're thinking about relative freezing points for a series of solutions like this. Okay. I'm not going to do this on this slide. So